Okay, hi everyone. So for today's problem session, I will focus on the galactic rotation, which is probably the most nasty part in your homework too. So I'll give a brief review on how to measure the galaxy rotation curve, and then give you some hint on how to approach the homework problem. Okay. Okay, so to measure the galaxy rotation, let me first draw a picture of our galaxy plane. So let's say here is our sun. And we know that the sun, the distance of the sun to the galaxy center is about 8 kiloparsec. This is, let's say this is R naught. Okay, and so we know that our solar system is also rotating around the galaxy, right? So there is a speed of our sun, and let's assume this is like all the orbits are circular. So there's a V naught, there's a velocity of our own solar system. And okay, so let's say, so there are two circumstances. We could be looking at the inner part of the Milky Way, or the outer part that have radius larger than our sun, right? So we will consider two cases. Right. So this one is the inner ring, and this is the outer ring. Okay. All right, so let's say if there is a star, let's say there's a star around here, which is on the inner ring. Okay, and so again, this star, it has a distance. We know the distance of star to the galactic center, right? And then this star also is rotating around the galaxy. So it also has a speed that is perpendicular to the distance to galaxy center. Say this is V, and the distance is R over here. Okay, so let's write all the parameters down. So now we have the R naught, which is the sun to galactic center distance, and V naught, which is the sun velocity, and R is the star to galactic center distance. And that star also has a velocity rotating the galaxy. Okay, so okay, so now we should know, it is important to know that to measure anything like in astronomy, like to measure the velocity in astronomical observations, it's important to know that we can only measure the radial velocity. So radial velocity means that we can only measure the velocity along our line of sight. So if we, there is also methods to measure velocity like across, like perpendicular to our line of sight, but it would take a huge amount of time to see a stellar object or something, like move only just a little bit. So it would take a lot of time. But like for spectroscopy, we can use Doppler shift to just like easily measure the velocity along line of sight. So, okay. So to measure the galactic rotation, again, the radial velocity would be a very useful thing to measure. Okay, so to measure the line of sight velocity, so here, the line of sight between our sun and the star would be this line over here, right? This straight line here is the line of sight. Yeah, so we're going to measure the velocity of this star along this line of sight. So it's not the red one velocity component. We should decompose it to the line of sight velocity and the other direction that is perpendicular to the line of sight. Okay, so so let's assume, so there's an angle between the line of sight velocity of the star and its real velocity component, right? And let's say the angle between this is let's say this is alpha. So yeah, and another angle we need to know is the longitude, the galactic longitude of this star. So galactic longitude is like starts from the direction of our solar system toward the galactic center. So this direction is 0 degree in longitude, and this direction is 90 degree. One 180. Okay. So so it's clear to see that the longitude of this star would be this angle over here, right? And we'll just call it L. Okay, so now, how do we represent the radial velocity of this star? So the radial velocity of this star, as I mentioned, is the line of sight component of the star velocity. But remember, we also have velocity. We are in the solar system. So we should minus that velocity with our own velocity in the line of sight direction, right? So, okay, so first let's do the line of sight component of the star. So we know the star has a velocity v, but we want the line of sight component, so that's cosine alpha. And we have to subtract our own velocity along line of sight, and that would be v naught sine L, right? Okay, I should probably, so it's V naught sine L because we decompose our sun velocity into this component perpendicular to the line of sight and this component. So this one is the line of sight component, right? And since this angle is also L, so we have to subtract V naught sine L. Okay, so this is our radial velocity equation. And so if we look at the triangle in the middle, which is like composed by the orange line and the blue line and the red line. This, if you look at this triangle and we use the law of sines, then we can write an equation like this. So we have R over sine L equals R naught over sine, that angle should be alpha plus 90 degree. And this is also cosine alpha, right? Sine alpha plus 90 degree equals cosine alpha. So just to make it clear, the angle here, maybe I should use a different color. So the angle here is alpha plus 90 degree. And this is because we know the angle between R and V is 90 degree, right? Because it's circular motion. And since there's an angle alpha here, so now we have the green angle to be alpha plus 90 degree. Okay. Okay, so with the sine equation, we can actually write cosine alpha as R naught sine L over R. And we can plug this into the radial velocity equation, and then we will get the radial velocity equals B cosine alpha, and we'll just plug in cosine alpha here. And minus V naught sine L. Okay, and then we can, so since there are both sine L in the two terms, we can extract R naught sine L. So the first term will be left with V over R, and then the second term will be V naught over R naught. All right. So this will be our equation for the radial velocity of a star at galactic longitude L and with a velocity V at radius R. Okay, so before I go on, is there any questions so far? Okay, if there's no question, the next step we should notice that if we are looking at different part of the galaxy, for example, the inner part of the galaxy or the outer part of the galaxy, there is actually different longitude range. So for example, if we are looking, okay, so let's look at this picture again. For example, if, okay, here is our sun. Let's draw a line here. Okay, so it is pretty clear that for a region beyond this line, it is always, if we look through this direction, then it's definitely the outer part of the galaxy, right? So this is purely outer part. But if we look on another side, we could be looking at the inner part or the outer part, right? So this one is inner plus outer. Okay, so to represent it as the longitude range, then it would be, so we can see if the longitude range is from 90 degree to 270 degree, then it would be purely outer region, right? So if we draw a plot of the horizontal axis is the longitude range, then we know between 90 degree and 270 degree is purely coming from the outer galaxy. Okay. Well, let's kind of write this down. Okay. Longitude range. Okay, and we will separate this as two different cases. Okay, so everything is back now, right? Okay, great. Okay. Okay, so where are we at? Okay, I see a question in the chat. Is alpha the angle between the two velocities? Alpha is the angle between the star velocity and the line of sight direction. And L angle between GC and object. So L is the angle, yes, it is between the galactic center and the star. And that is called the galactic longitude. Does that answer your question? Okay, great. So let's move on. So, so as I said, there will be a limit for the longitude range in the inner part, if we look at the inner part of the galaxy. And the so the limit for the inner ring, there will be a maximum longitude we can see. And I'll explain why shortly. Okay, so, and this Lmax should be less than 90 degrees. Okay, why is that? Because, so if we're looking at the inner part of the galaxy, let's say, is there any more color? Okay, let's use blue. So if we are looking at the inner circle here, and we are looking from the sun, you can see that there's actually a range. Oh, I probably shouldn't use blue. Wait, okay, I'll just use white. So there is a range, the longitude range, where we can see this inner circle, right? So this maximum longitude would be this line and perpendicular to the distance to the galactic center, right? So at this point, is the maximum longitude that we will see for any object on this inner circle. So that's why there is a maximum longitude range for any inner circle. Okay, and how about the outer ring? For outer ring, so as I mentioned before, so outer part of our galaxy is like everywhere, right? From 0 degree to 360 degree, right? So at any angle, we could see galaxy from the outer part. But as I mentioned before, from 90 degree to 270 degree, it is purely from the outer part, right? Okay, so let's write this down. For outer ring, we can basically, so basically everywhere could be coming from outer part, but from 90 to 270 degrees, it is purely from the outer ring. And from 90 degree to negative 90 degree, it could come from both inner and outer part. Okay. Okay, any questions so far for this part? Okay, if no, so for the homework problem, so let me see. So the homework problem gives an assumption of if the rotational velocity is a constant everywhere, then what will happen, right? So, okay. So let's do the same for the homework problem. So given that V of R is constant everywhere, and the number for the homework is like, so this is actually about 200 to 220 kilometers per second. And this velocity is actually the velocity, approximately the velocity of our solar system, which is V0. Yeah. So when we do astronomical observations, we actually use, we usually use the local standard of rest frame, which is called VLSR, and we measure all the astronomical objects in this kind of unit. So yeah, so this about 200 kilometers per second is the mean velocity of our local standard of rest frame. Okay, so now we're going to use our radial velocity equations, which is above right here. Okay, we will write VR, radial velocity is R0 sine L, V over R minus V0 over R0. Okay, but since now we assume the velocity is constant everywhere, right? So this means that V equal V0 equal constant. Okay, and so this can be reduced to R0 sine L, and if we take V out, it will be 1 over R minus 1 over R0. And this can be further reduced to V sine L, and we'll put R0 into the, so it's R0 over R minus 1. Okay. So we'll use this equation. Okay. So the reason why I reduced the equation to this form is because you can see there's a R0 over R term, right? And that term actually depends on whether we are looking at the inner ring or outer ring. Okay, so for the first case, if we're considering the inner ring, then we will have R less than R naught, right? Because it's in the inner part. And that would make the term in this term larger than 0, right? Okay. So this is the first constraint from the, if we're looking at the inner part of the galaxy. And the second constraint is, as I said, there's a longitude range if we're looking at the inner ring, right? So that for the inner ring, our longitude should be between some values. And okay, so I mentioned that this term is always larger than 0 in the inner ring. But how about sine L? So sine L could be positive or negative, right? So that's why we need to consider the longitude range. Okay, so we know sine L is negative if L is negative, right? So if we have L negative, which is in this range, then we will have sine L negative as well. But if we have positive L, then sine L is also positive. So, okay. So here for inner ring, we always have this term positive. And this means that if we're looking at the inner ring and the longitude is the longitude is negative, then it means we will get a radial velocity less than 0. But if we have a longitude, positive longitude, then we will get a positive radial velocity. Okay, so this is very important because we measure the radial velocity, right? And you should know which part you're looking at. If you measure a positive radial velocity, and what does it mean and where does it come from? Okay, so this is for the inner ring part, and let's consider the outer ring. Okay, for outer ring, we have R larger than R naught, right? So we have R naught over R minus 1 less than 0. Okay. And then second, we consider the longitude range. And as I mentioned above, L could be at any angle because it's from the outer part. But what we really care about is the sign. It's the plus or minus sign of the sine function, right? So, okay, so sine is positive if L is positive. So that means if L is positive, then sine is positive. And in the other half plane, L is negative, right? That means sine L is less than 0. Okay, so again, we can do the same thing. For outer ring, we always have this term less than 0. So if we combine this, so if we have L in the positive plane, then we will get radial velocity less than 0. But if we have negative L, then the radial velocity would be positive. Okay, so I I remember it's part B of that homework problem. So you are asked to draw a plot of the velocity versus the longitude range, right? So this can actually tells us, so if we draw the plot here, and this is longitude, and this is velocity. Okay, so the longitude, this is 0, and let's say this is plus or minus 90 degrees, and this is the edge. Okay, so so for this range, it's actually 180 to 360 degrees, which is the lower half plane. Okay, yeah. So this means, so let's see what we have. So for the inner ring, we know there's a limit of the longitude range, right? So let's say, and that longitude range should be less than 90 degrees. So let's say here, something here is, okay, they should be symmetric. Okay, I'm not drawing very well. Okay, so let's say this is the longitude range for a specific inner ring. Okay, and what do we have for inner ring? So if the longitude is between 0 and negative L max, we will have radial velocity less than 0, right? So that means this region. For inner part of the ring, we should only get components in this region, not in this region. Okay, and if we have a longitude larger than 0, then we should get radial velocity larger than 0, which is this part, right? So nothing here. Okay. Okay, so this is, so the blue color indicates the inner ring. So the reason why I'm mentioning this is because, like, when you do the homework problem and draw the plot, if you find that you are drawing a plot for the inner ring, if there's any component here, then it means you should probably recheck your calculation. Okay. So okay, so for the outer ring, as I mentioned before, for the 180 to 270 degree, it is purely coming from the outer part of the ring, right? So that is this part and this part. So these parts are coming from purely outer part of our galaxy. Okay, so let's see what will happen if, for the outer ring, if we have longitude of between 0 and 180 degree, then we will get a negative radial velocity, right? Okay, so we will get something here. And otherwise, we will get a positive radial velocity. So that means something here. This color is for the outer ring. Okay, so so we know that if we combine the inner ring component and the outer component, then basically within the range of L max, we can see both components, like from either the inner part or the outer part. But but between the 90 degree to 270 degree, it's only coming from the outer part, right? So this means that in this range, we will only see component with positive velocity in this range and negative velocity in this range. All right, but for the range inside the L max, we could see from either component, but you should be able to distinguish that positive or negative velocity corresponds to which region. Okay, yeah, so this is basically all I want to say today. So is there any question for the problem session?
Yeah, so about Lmax. So for the inner ring, we have to find the range, but for the outer ring, it's always the same. It's the one that you've given, right?
For the outer ring, it's not like always the same. It's everywhere, right? Like you turn around 360 degrees, you can, like, basically the outer part is coming from every direction.
Yeah, that's probably why I had trouble applying the same formula for the inner ring that to the outer ring, because I had like a sinus that is out of range. Okay, thank you.
Okay. And for those who didn't come last week, so basically the later half of the problem session would be just like office hours, so you could ask any question on either the problem session, or if you have homework problem to ask, you can also. Okay, I see a question. Could you go over alpha again, please? Yeah, so alpha is the angle. Okay, maybe I should write this down. Okay, alpha is the angle between the velocity of the star and the line of sight direction. So, so it's this blue line here, line of sight.
Oh.
Yeah, between V and that blue line. Okay. Yeah, I should.
Would it be generally like very small, or at least in this case, it would be very small?
In this case, it is very small.
It could be really big if it's the velocity is like perpendicular.
Yeah, exactly. If the velocity is perpendicular, then the line of sight velocity would be 0, actually.
Oh,
yeah.
True.
Yeah.
Okay, thank you. That helped a lot.
Yeah, no problem. So I should write, okay. L is the longitude, and alpha is the line of sight. B.
Okay, thank you.
Yeah, sure, no problem.